Okay, let's talk about unique binary search trees too. So this question is pretty similar to 96, which is the first version of unique binary search tree. So if you didn't watch it, just go back to watch. And for this question, the thing you have to do is you have to create a tree instead of like output a single integer number. So what you actually need to do is you need to like traverse on your left subtree and right subtree for each of the root. So your root 1 will have 2 possible, right? Root 2 have 1 possible, and roots 3 have 2 possible way. So the total answer will be 5, but you have to return the list of the list. And before I dive into the solution, let's just look at this guy post. So give this guy credit. So you have to create a root node by cycling through start and end or one to end. So recursors generate all possible left subtree by root of the binary search tree. All value in the left subtree are less than the root. Those use the list start and then the the current root -1 to create the left subtree, and on the other hand, the right subtree is from current root +1 to the end. So for each combination, left and right subtree attach them to the current root to form a unique binary search tree. So just attack to the end, and they just code it and think about what happened next. So let's do it. So what I would do, I would create a helper function. So before that, I have to say if n equals 0, I have to return just a new array list. And there's no point when n equals 0. So I have the 1 to n, right? So I'm going to create a helper function, which is list of tree node, right? And what I have is I have the star, I have the ends. So I'm going to return a helper function, which is type list of tree node, and I'm going to create my list of tree node over here. So I will return this value, list of tree node. I'm going to say list equal to new array list. So there's one possible way for when star is greater than n. I mean the base case, you have to return. So you have to add something which is null. I will talk about this later, and return this. So this is the base case, but I will talk about what happened. So now you have to traverse, right? So how can you actually know like your root value? So then you have to traverse from start to the end, right? Has to be less than equal. Come on, less than equal to n and I plus plus. Now, for every single root, right? For every single I, you have to be a root. So I have to say list tree node. I'm gonna say left subtree, right? Equal to you're going to call your function from the start to I -1. Your current root is I, and then your current root is I, and the left subtree is from start to I -1, and the folder will will linearly growth, right? So we're linear increasing. So you don't care about when I equal to start. So when I equal to start, it doesn't actually matter, but this is how it actually starts from. So I also have less subtree. I'm going to call myself an I +1 to n. This will generate the left subtree and right subtree. And once you have it, you just traverse tree node left on left subtree and tree node right on right subtree. So hopefully I don't make a typo. So once you have it, you can create a tree node. So I'm going to say node equal to new tree node. So what is your value. Your value should be your root, right? So your value is equal to I. How about your left and right? Left and right is your the node from left subtree and right subtree. So once you have it, then you can add to the list. At the end, you just return list. So let's think about how we actually do it. So before we go into it, we have to look at the diagram. So when n equals to 3, right? When n equals to 3, root 1 have two possible ways. It's either 1, 3, 2 or 1, 2, 3. And root 2 has one possible way, which is 1 on left, 3 on right. And 3, when 3 is the root, there are two possible ways. So when you actually do this, you are collecting the combination of left subtree and right subtree, and you just have to generate all possible ways. And then you add to the list. When you add to the list, that would be the answer. But since you keep calling yourself, right? I mean, once you keep calling yourself, you are going to turn out star greater than n, and this is how we actually how we avoid. So this guy is actually save everything. So if you have time to read over the article, just please go ahead. So start from here. So when we current root is the I, okay, equal to star. So we call helper function, and current root value equal to n, and we call helper function plus 1 n. So in both cases, helper function, star is greater than n, which will cause the for loop to not run. So if the for loop is skipped, we return O3, which is the empty list. Thus, if the of left subtree, which is the starting to I minus 1, return empty list, the current empty list will happen when we reach the inner for loop. So the inner for loop is actually this. So inner for loop, right? So this loop will not run because it's empty. If it is null, it can still be run. And then we can also traverse the tree node on the right subtree. This is how we actually know. So we have to collect a combination and then just run it. And then I made a typo, which is this. Sorry. And hopefully no typo. Okay, yeah. Well, that's good enough. So let's talk about time and space complexity. I will definitely forget the solution later, but once I have done this question, I can try to remember. So the time complexity and space complexity is based on Catalan number stuff, because you are going to recursive call yourself, and this what you call this recursive function is actually based on Catalan numbers. So just go on Wikipedia, type Catalan numbers, and you will find out for this function, for this question, is 4 to the n over n to the 1 over 2. That is the time and space complexity. And don't ask me how I get it. I definitely just read the article and take the answer from the article, because it's so hard to explain. And I hope you get it. And let's see, you have any question, just comment below.